Hello and welcome. Have you ever looked at one of those colossal container ships, a literal floating city made of steel, and just wondered, how on earth does that thing stay afloat? It really seems to defy all common sense. Well, in today's explainer, we are going to unravel that exact mystery, all with a little help from the beautiful principles of physics. Okay, let's just dive right into the heart of the problem. This is the big paradox, right? You can take a tiny pebble, toss it into a lake, and poof, it sinks straight to the bottom, no questions asked. And yet, a massive ship weighing hundreds of thousands of tons just bobs along on the surface like it's no big deal. So what is going on here? How is that even possible? To get to the bottom of this, we're going to follow a really clear path. First, we'll tackle the paradox itself. Then, we'll uncover this invisible force called pressure. After that, we'll meet a genius from ancient Greece. And finally, we'll put all the pieces together in what I like to call the Great Balancing Act. Think of each step as a clue that gets us closer to solving the puzzle. So let's kick off our investigation by really digging into this puzzle of the ship and the pebble. To really understand why anything floats, we have to start with the water itself. You see, all fluids, and that includes water, are constantly pushing. They exert this unseen force that physicists call pressure, and this is the first major key to cracking our case. So, what is pressure, really? Well, it's just a measure of how concentrated a force is. The formula is super simple: force divided by area. Think of it like this. A sharp needle is going to exert way more pressure than your flat palm, even if you push with the same force, just because all that force is focused on one tiny, tiny point. And this slide illustrates that perfectly. If you've got a force of 40 newtons, that's roughly the weight of a gallon of milk, and you spread it out over a big 5 square meter area, the pressure is a tiny 8 pascals. We're talking a very gentle, very distributed push. Okay. Now, what's really cool are the properties of pressure in a liquid. But for our mystery, one of these is the absolute game changer. Just look at that first point. Pressure increases with depth. The deeper you go, the harder the water pushes. I want you to burn that into your brain. It is the secret ingredient, and it leads us directly to a famous eureka moment from over 2,000 years ago. So that secret ingredient we just talked about, the fact that pressure increases with depth, is the entire reason for this powerful upward force that fluids exert on anything submerged in them. And here it is, the legendary Archimedes principle. Basically, what it says is, when you put something in water, the water pushes back. This upward push is called upthrust or buoyant force, and what Archimedes figured out is that its strength is exactly equal to the weight of the water you just pushed out of the way. This upthrust, this is the hero of our story. But why does it even happen? I mean, it's not magic. It's a direct result of what we just learned. Because that pressure increases with depth, the water at the bottom of an object is pushing up way harder than the water at the top is pushing down. So the net result of all those different pushes is one big push straight up. You felt this? This is exactly why you feel lighter in a swimming pool. Your real weight hasn't changed, of course, but the water is literally helping to lift you with its upthrust, so your apparent weight feels like it's less. That buoyant force is doing some of the work for you. And this isn't just a cool fact for the pool, it's a really practical tool. Scientists can figure out the exact upthrust on an object just by weighing it in the air and then weighing it again in water. That difference between the two numbers, that is the buoyant force. So now we have our two competitors, the downward force of weight and the upward force of upthrust. So what happens when these two forces face off? Well, that's what flotation is all about. It's time to finally solve this paradox. Okay, here's the crucial part. Floating is just a perfect balance. An object floats when that upward push from the water is strong enough to perfectly cancel out the downward pull of its own weight. It's like a cosmic tug-of-war, and floating is a perfect tie. And here it is, the final showdown. Just look at the pebble. It's small, it's dense. Its weight is way greater than the tiny bit of upthrust it can generate. Gravity wins. Every time. It sinks. But now, look at the ship. Yeah, its weight is absolutely immense, but because of its shape, it generates an equally powerful upthrust. The forces are perfectly balanced, and so it floats. But how? How in the world can a ship create that much upthrust? Well, it's all about the shape. It's an engineering marvel. If you just took a solid block of steel that heavy, it would sink like our pebble. But by shaping that steel into a massive, hollow, really wide hull, engineers make sure the ship shoves a gigantic amount of water out of the way. And all that displaced water has an enormous weight, which in turn creates an enormous upthrust. The shape is the whole trick. So let's just recap the three big ideas real quick. First, you've got pressure. The force water exerts, getting stronger the deeper you go. Second, upthrust, that upward force created by the pressure difference. And third, flotation, that beautiful equilibrium that happens when an object's shape lets it create an upthrust that perfectly equals its own weight. So the next time you see a giant ship, or maybe an iceberg floating with just its tip showing, or even a hot air balloon rising up into the sky, you'll know the secret. It's not magic. It's just a beautiful, elegant balancing act of forces. So, what else out there in your world is secretly governed by this same principle? Thanks for tuning in.